Hey guys, so in this video I have another thing to add to our idea of a Hilbert space. So if you remember, a few videos ago we started adding the idea of complex numbers in, and now I'm going to add in the idea of having more than two dimensions, right? Because not every discrete quantity in quantum mechanics is going to is going to just have, two outputs. It's either black or white, right? If you think about energy, right? If you think about the energy of like a atom and hydrogen, right? If you remember that formula, it had some energy E naught divided by n squared, right? So there were discrete energy levels, right? But but there were really an infinite number for any possible n, right? So we have to account for that now, right? And expand our idea of a Hilbert space into multiple dimensions, and it's really not that hard. So you'll see. So really, what I'm going to do, right, is just say that. So I've got psi is equal to, well, instead it's not just going to be c1 phi1 plus c2 phi2, right? And again, it's still complex numbers, right? So what we've done, it still holds. But now, well, why can't we have a third option? C3, C3. Right? Imagine, think about our, color and hardness thing, but imagine now there's a third color it can be. Right? Imagine it could also be, say, green or red or something, right? So we can add even, or right, as many dimensions as we want to correspond to some quantum property with more than two possible outcomes, right? And so this, you can write this in sigma notation, and I mentioned sigma notation in our math videos. It's just summing things up, summing up for all possible values of j. J is just our counting variable of Cj v sub j, right? And the probability, in this case, the probability, it's going to be the same thing with the norm squared. So the probability that if we measure, and I'll note right here, this is q sub 1, right? This is the state, phi 2 is the quantum state with q sub 2, quantum state with q3, q4, etc. This is the quantum state with q sub j, right? So the probability that if we measure big Q, we'll get little q sub j, which is the observable, right? Or this is the quantity of the observable big Q. This will be the norm squared of c sub j, right? And this can be 1, 2, 3, however many possibilities we have, right? And so, for energy, this j would be, n. It would be the energy level that we're at. So this is pretty simple, right? Now we'll note that, and hopefully you're familiar with this. If not, I will have a link in this video, or a link in the description, about how to get the length of like a three-dimensional or a four-dimensional or a higher dimensional vector, right? And it turns out Pythagorean theorem, right? So if say I've got some vector v, just a quick side note, is I don't know, Vx, or I'll actually do this. So it's V1 times I hat plus V2 times J hat plus V3 times K hat, right? Where K hat is the unit vector in the z direction. Plus, we can come up with even one more. V4 times L hat. And this is J hat. N plus V5 times M hat. You can go on. You can go on, and it turns out that the magnitude of this vector is going to be the square root, just like in Pythagorean theorem, right? Or we can actually say, probably even better to say, the magnitude of this vector squared is equal to V1 v1 norm squared, right? This accounts, so ordinarily it would just be v1 squared plus v2 squared plus v3 squared plus v4 squared plus v5 squared, however many you have. But instead this time, because we can be dealing with complex numbers, we'll have the norm squared, and I explained that a few videos ago, I believe. So v2 squared right, plus v5 squared, etc. So the magnitude of a vector has a very similar form in more than one dimension, and I'll have a video explaining this in the description. It's not too hard, and if you don't want to look at that video, you can just sort of buy that this is true. So additionally, right, we can define a dot product in more than one dimension. Remember, if you remember the dot product, right, if I've got, vectors in more than in vectors in 2 dimensions, right, the dot product is just, let's say I have a vector is equal to ax times I hat plus ay times j hat, and b is bx times I hat plus by times j hat, right? A dotted on b would just be ax bx plus ay by, right? And so now if I add in a third, right, a z k hat, bz k hat, you would get this, or sorry, not equals, you would add another term, right, a z bz, and it would just be, right, etc., etc. So that's just expanding sort of our vector properties into multiple dimensions. Hopefully you're familiar with this. May have even mentioned this in our vectors video. Right, and so we can express that the magnitude of psi, right, norm squared, is equal to the and just note, this is our superposition, right? This is expressing psi in some basis of the observable Q, right? This is our superposition. And then we can express the magnitude in terms of the superposition, magnitude of psi squared. This is just, right, the, remember, because each of these are unit vectors, right? So just like what we did here, we're just going to sum up, right? Or I'll express it a little bit more explicitly here. Will be, right? Oh, and I forgot right here. This is a plus dot dot dot. Hopefully you caught that there. So this is C1 norm squared plus C2 norm squared plus C3 norm squared plus dot dot dot. This is equal to the sum over all possible values of j. Right? This is how we'll write it. We're not going to write j equals to 1 to infinity, because this is just a shorthand of saying all possible values of j, right? Whether we're starting from 0 or 1 or 2, any possible value of j, we're summing them all up. And this will be the sum c sub j norm squared, right? But notice, this sum is also the sum of all the probabilities. So again, just like we had before with normalization, this must be equal to 1. Right? And so we can then define our, I'm going to erase this down here, hopefully you've got that, define our inner product postulate in 3 dimensions. Think about how I proved it in 2 dimensions, and given that this is, and we'll see it's called an orthonormal basis. Actually, I'm going to do the orthonormal basis first. And then I'll show you what I was saying. So keep that in the back of your head. We've got to generalize our inner product postulate that we've had before, that we developed, I believe, in the last video, and I proved. We've got to expand that into the domain of more than one dimension, right? And also note, even though beyond 3 dimensions, it's going to be really hard to graph it, right? Now that you sort of understand how the Hilbert space is graphically, and you understand it mathematically with these vectors, and just basing off dot products, you don't really need to graph it in 4 dimensions or 5 dimensions, right? And even though it's hard to think about, right? Who says that, because we can only graph in 3 dimensions, energy can only take on 1 of 3 values? No, it can take on 4 values as a 4th energy level, a 5th energy level, 6th energy level, you can have as many as you want, and it's still got to obey this Hilbert space, right? Because and I kind of implied this, but just to sort of state explicitly, pretty much all of these discrete quantities in quantum mechanics behave the same way as color and hardness behaved back in our video on the Stern-Gerlach experiment. And they all kind of work in this Hilbert space. The Stern-Gerlach experiment was just the best way to show it. The Stern-Gerlach experiment was done with one specific quantity, but we do know that all of the quantities, at least these discrete ones, and we'll get in the next section about continuous quantities, but all the discrete ones obey this kind of Hilbert space idea. Okay, so I'm going to erase this. Hopefully you've got it down. And so when we make this basis, right, in quantum mechanics, we want to have what is called an orthonormal basis. Right? And what that means is just like what we kind of had with unit vectors, right? The unit vectors form an orthonormal basis, right, in 2 or 3 dimensions, and you'll see why. So the first thing is all the vectors, right, the basis vectors, right, the phi1, phi2, phi3, phi4, right, all of those have to be perpendicular to each other, right? Otherwise, you know, otherwise it wouldn't make too much sense, right, with our probability inner product postulate, right? Because if the inner product, but say you know phi1 and phi4, if you took their inner product, right, that's got to be 0, because if it's in the state phi4, the probability that it has q1 is equal to 0 because it has q4, right? Hopefully that makes sense. And then you may want to replay that, rethink about that, make sure that does make sense to you, right? So what this is what this is saying is if I've got phi m, phi n, right, this must equal 0 if m does not equal n, right? And so, right, because otherwise, if these are not the same basis vector, they've got to be perpendicular, right? And if they're perpendicular, their inner product is 0. The other thing to note, right, about an orthonormal basis, first of all, this is called orthogonality. Right, this is called orthogonality. And so, you know, psi1 or phi1 and phi2 are orthogonal because they're perpendicular. Orthogonal is another way of saying perpendicular. Now, if I have phi m inner product with phi m, right, this is phi m norm squared, right, which is, if this is a basis, if this is, you know, a unit vector, this norm squared has got to be 1, right? And so this is called normalization. Right? And so orthonormal, orthogonal, and normalized, right? Orthonormal, that's just a combination of these two. So if I have phi m inner product with phi n, right? This is equal to 0 if m does not equal n, and 1 if m does equal n. And we actually have a mathematical notation for writing it. It's called a Kronecker delta, and it's just delta with lowercase Greek delta with the subscripts mn. And literally, this looks a little bit complicated, but all it means is it's 0 if m does not equal n, and 1 if m does equal n. So this is just a shorthand of writing it. And this is our orthonormality condition. And this is just saying that all the bases in quantum mechanics have to obey this. Given this orthonormality condition, right, your task here is, and this is not too hard, and you can look at how I proved it in 2 dimensions, and it's the same exact proof in 3 dimensions. to show that that probability postulate, right, holds, right? If I've got psi is equal to, um, if I've got psi is equal to C1 phi1 plus C2 phi2 plus dot 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 is equal to, right, sum over all values of j, Cj, phi j. Given the orthonormality conditions, right, showing that if I've got phi j, and you can prove this with anyone, so this could be phi1, phi2, phi3, whichever one, it will work for any of them. Inner product with psi is equal to Cj, right? So like phi1 inner product with psi will be phi1. Similarly, we know that psi inner product with phi j would be Cj star, right? You can show that, and then you could see that the probability of q sub j would then equal, just because we know this is sort of how we're defining probability, this would be the norm squared of phi j psi, right, which is equal to the norm squared. This is equal to this, which is also equal to the norm squared of psi phi j, right? Just because they're complex conjugates of each other, and the norm of a complex conjugate is the same as the other thing's norm, right? Right. The norm of this, the norm of Cj, and the norm squared of Cj and the norm squared of Cj star are the same. Okay, it's just one of our properties of complex numbers. Okay, so back to my last two notes. So the first thing is about phases. If you remember, I talked about phases, right? And if I have an orthonormal basis, right? If phi1 or phi m is orthonormal to it, so if phi m is orthonormal to phi n, then then phi m is also orthonormal so then phi m is also orthonormal to phi n times a phase, to lowercase p, remember that's a phase, times phi n, right? Where this phi is equal to just sending e to the I theta, right? And you can show this, right, just by showing that the inner product, right? Remember the phase is just a constant scalar, right? So you can take it outside of the inner product by our properties of inner products, right? And so you can actually prove this. I'll do that briefly here, right? Right, and so this just shows that you can multiply any of the basis vectors in a basis by a phase, and it will still be, so if I've got an orthonormal basis, and this is important, you'll want to write this down. If I have an orthonormal basis, and I multiply any or all of the basis states by phases, right, they can be the same phase or different phase, the basis will still be orthonormal, right, because this phase won't change any of our conditions. If I've got phi m inner product with phi n, right? And also note, I didn't mention this before, I figured it was pretty obvious, but I'll just say explicitly, if phi m, phi n inner product, if their inner product is equal to 0, then the complex conjugate of 0 is 0, so that would mean phi n inner product with phi m is also 0. Right? It's perpendicular, it doesn't matter what order. And so phi m, phi n, right? Or actually, phi m, and I'll use that bad notation that I mentioned. because it's generally what's used, times a phase, inner product with a phase times phi n, right? This is, well, the phase can get taken out of the inner product by one of our properties of inner products, right? This phase, I'm really bad at lowercase p's. I don't usually make a difference. I just had to make a difference here just because I didn't want to confuse it with probability, so I wanted to kind of overstate the difference here. Um, so, right, you can take the phase out, phi m phi n, which is equal to 0, right, assuming phi m and phi n are orthonormal. And same thing here, if I have a phase times phi n, right, and a phase times phi n, right, if I'm multiplying these two together, this is just phi n, the phase times phi n, phase times phi n norm squared, and gotta just make it in a ket vector, norm squared, right, which is equal to the phase norm squared times phi n norm squared, right? Hopefully you can follow this. I know it's not super neat, but this is just equal to 1, right? The norm squared of a phase is 1, and we also know that, right, this is equal to phi n norm squared, but if I said that they are orthonormal, right, if phi m is orthonormal to phi n, that means phi n, right, is its norm squared is 1, right? So this would be equal to 1, right? So that's the proof, right? So again, that statement is if I have an orthonormal basis and I multiply any basis vector of that, any basis vector or all of them or however many of them by some phase, doesn't have to be the same phase, right? The basis is still orthonormal. Erase this. The last really brief point I want to make is called the Cauchy inequality. I will have a link in the description to the proof for it. But if you think about a dot product, right? If I've got A vector dotted on B vector, this is magnitude of A, magnitude of B, times the cosine of the theta between them, right? And right, and so it's necessary because the cosine theta, the highest it can be is 1, right? So that means, right, A dot B must be less than or equal to A magnitude of A times the magnitude of B, right? You know, the absolute highest, right? The absolute highest this A dot B can be is A times B. Otherwise, A dot B is going to be less than A times B if the cosine of theta is not equal to 1, right? And it's the same thing, right? If it's negative 1, then A dot B is going to be negative A times B. So actually we can put this in absolute values too, right? Because if we have this here, right, it's just that's all that would make a difference, right? So hopefully this makes sense, right? A dot B is less than or equal to A times the magnitude of A times magnitude of B. Similarly, with complex with inner products, this works because the inner product, right, is just a is just an expansion of the dot product. So it should be true that if I've got I don't know, something A inner product with B, this is less than or equal to A norm squared times B, or sorry, not A norm squared, A norm, the norm of A times the norm of B, right? But we can square both sides, right? A, or take the square of both sides. A inner product with B. Oh, sorry, I forgot the absolute value. That's what I was missing. Okay, so if I take the norm squared of both sides, A inner product with B norm squared is less than or equal to, right, A norm squared times B norm squared. Right? I hopefully followed the logic of why this inequality works based on this equation, right? You can sort of test out some values of cosine of theta, any value of theta, and you'll see that this works. That's a good way of proving it. This equation may be a little less intuitive. It comes from this, but there's another proof. I'll put that in the description. I just wanted to mention this because I will be using it in video 2.9. Okay, I will see you in the next video.